Hi, my name is Peiqi from MIT. I'm presenting our work on sample-specific debiasing for better image-text models. Self-supervised representation learning on paired image-text data uses text as labels, requiring no further annotation beyond what has been routinely documented. In our case, a neural network is trained using contrasted learning, a particular type of self-supervised learning on paired image-text data. Once a model is properly trained, we can use it to a bunch of useful tasks. For example, we can use it to retroactively classify images to select relevant patients for a clinical trial, enable informed interpretation of medical images by retrieving similar patients from a database, help physicians verify the accuracy of a report by noting whether the referred location or visual grounding of the text is consistent with their impression of the image. Contrasted learning involves contrasting semantically similar or positive and semantically dissimilar or negative pairs of data points. To compute the contrasted loss, we start by sampling a piece of text from the data. We treat its associated image as a positive sample. Finally, we draw images uniformly from the dataset and treat them as negative samples. However, doing so introduces false negatives, samples that are treated as dissimilar samples from X, but belong to the same class as X, in this case, cardiomegaly. To improve the quality of the learned representations, we developed a novel approach that corrects for false negatives. Debiased contrasted learning optimizes the asymptotic debiased contrasted loss, where the second term of the denominator is an expected value with respect to truly negative samples. The expected value in the denominator can be estimated with an estimator G, using extra positive samples to offset the influence of the false negative terms. Eta is treated as a hyperparameter and is assumed to be a constant. However, the choice of a constant eta can be suboptimal when the underlying class distribution is non-uniform, as is commonly the case with healthcare data, where most data points belong to a few common classes, while the remaining data points are spread across many rare classes. We propose to estimate sample-specific class probabilities, the latent class probability of each data point, to appropriately compensate for the effect of false negatives. In particular, we employ the likelihood of the text provided by a language model to construct the class probability estimate eta x of x. Substituting G in the denominator, the resulting loss function can be viewed as a variant of debiased contrasted loss that uses estimated sample-specific class probabilities. We also show theoretically how choices of the sample-specific class probability function affect the approximation error. Our method, shown as dotted blue line, outperforms debiased contrasted learning that applies a fixed amount of correction to all samples, and baseline that does not correct for false negatives. Debiased contrasted learning with sample-specific debiasing outperforms state-of-the-art baselines as well as alternative approaches to false negative correction. Drop by our poster for more details.